Hello everyone, I'm Dr. Janki Vimani. Today I'm going to talk about disjoint set, also known as union find. We are going to look at different optimizations such as path compression, union by size, or union by rank. We are going to look at specific implementation or application of disjoint sets, as well as we'll learn about time complexity analysis of different operations. Ready? So, what is a disjoint set? It is a data structure which helps us to manage and track a collection of non-overlapping sets. That's basically if we have different sets with different elements, let's say 1, 5, 3 is one set, and we have another set with 9 and 11. We would call this as two different sets with non-overlapping elements. So what are the different operations that this data structure performs? Mainly two, find and union. Find basically helps us to identify which set does the element belong. For example, find 3. If 1 is the representative of this set, would return 1. Find 9. If 9 is the representative of this set, would return 9. What are the use case of disjoint set, or where would we use this data structure? Popular Kruskal's algorithm uses disjoint set. Implementation of minimum spanning tree can be done using disjoint set. Also, there are many other applications, such as finding cycles in an undirected graph. Okay, so now let's understand disjoint set operations, find and union with a specific example. Let's say we have 5 different elements with each of this as disjoint set by itself with single element in it. Now, if you want to perform range of operations on that, so here, if we want to perform union of 2 and 3, that would combine these two sets into a single set. If we want to perform union of 1 and 4, that would do the same to 1 and 4. Now we have 3 different sets in total. Then if we want to perform find 3. So let's say that 2 is the representative of this set, 1 is the representative of this set. And then the find 3 operation would return 2, would return its representative of that set. Then if we want to perform union of 1 and 5, that would basically merge these two sets. So that would make our sets look something like this. After this, if we want to perform union of 5 and 3, then that's basically merging these two sets that we have. So that would make a single set. And now let's say that 1 is the representative of this combined set. Finally, if we want to perform find 4, that would return 1, which is its representative. So these are simplistic operations. Now, what is path compression? Let's understand that. So instead of find 4, or let's say after find 4, if we have another operation, find 3, right? So then find 3 would definitely return 1. But with the path compression optimization, what would happen is we would detach 3, because in order to find the root of 3, we would have to traverse to 2, then 5, and then we would know that, okay, 1 is the representative and we would return 1. Now, we don't want to do this lengthy string of operations every time when we have to find 3. So, whenever a find 3 operation is issued with the path compression optimization, we would detach 3 from there and we would attach it directly to the root. Now, next time, whenever find 3 operation is issued, the time complexity of finding the root element of that set for find 3 is just constant, right? So that's where it is optimization. Okay, so next, after understanding the path compression optimization, let's understand the optimization of union by rank or union by size. Now, as the name goes, right, the rank or the size. Rank is basically what's the height Okay, so now after understanding the optimization of path compression, let's understand the optimization of union by rank or union by size. Let's say the rank of this tree over here is 2, right? And then we have another set. So let's say if we call operations such as make set, let's call elements as 11, 9, and 6. So that, and let's say that the representative of this set is 11. So that will make us another set, something like this. Okay. Now, once we have this set, representative is 11. So if we are representing this by tree structure, we would have its parent for each node. We would have the Okay, so after understanding the path compression optimization, let's understand what is union by rank or union by size. Now, let's say we have a bunch of more elements. For example, 6, 7, 8. Again, each of it is set by itself. Now, if we call operations such as union 6 and 7, that would join this both. Then if we call union 7 and 8, that would basically join this both. And let's say the representative of this new set is 6. Now, after this, if we have an another operation, let's say union 8 and 2. So basically now we have to merge these both trees that we see over here. When we call it as union by rank, we compute the rank of this tree, which is 2. We compute rank of this tree, which is also 2, right? So then in that case, when we merge it, it does not matter if we attach this to this or this to this. But let's say if we are doing union by size. So then the size of this tree is number of elements in this tree, 1, 2, 3, 4, 5, right? And the size of this tree is 3. And if we call union by size, so then we attach the smaller tree to the larger tree. So with union by size, our combined tree would look something like this. And now let's say if we call operation find 8. So basically it will find its parent, then its parent, then its parent until it reaches the representative element of the set. So it would return 1. And with path compression optimization, what will it do? With path compression optimization, it will take this 8 and attach it directly to the root of the set, such that next time, whenever we call find 8, rather than doing all this bunch of operations, it is directly able to reach to the representative of that set. Okay, so now let's look at the time complexity and space complexity. Space complexity is simple. If we have in total n elements, then the space complexity of disjoint set with n elements is big O of n. Time complexity is big O of m alpha n. What is m? M, let it be total number of operations. Okay, now let's understand the space and time complexity. Space complexity is simple. If we have in total n elements, then the space complexity of a disjoint set with n elements is big O of n. Time complexity, if we have total m operations, with each operation being things like union, find, right? Bunch of these. So if we have total m operations, and if these operations are performed over n elements, then the time complexity is big O of m multiplied by alpha n. What is alpha? Alpha is inverse Ackermann function, which is basically a function that grows at a very small constant rate, almost equivalent to 4. So that basically makes our time complexity as big O of m multiplied by 4, which is nothing but big O of n. Okay, so now let's understand the space complexity and the time complexity. Space complexity is simple. If you have n total elements, then the space complexity is big O of n. Time complexity, if we have in total m operations, where operations are nothing but basically these things that we perform, right? Union of 2 comma 3 is a single operation. Union of 1 comma 4 is a second operation, and so on. And if we have total n elements, then the time complexity is big O of m alpha n. What is alpha n? Alpha n is a function, inverse Ackermann function, which basically grows at a very small constant rate. So alpha of anything is basically a constant, which then reduces our time complexity to be big O of n. All right, so next, let's learn about the implementation of disjoint set. Three things which matters to us while implementing disjoint set is the value of the element, the parent of the element, and the rank or the size based on whatever we want to perform that algorithm with. If we know these three things, then we can perform different operations that we discussed earlier. So as we see in the code over here, to initialize the class disjoint set, first we would initialize each element to be its own parent. So basically we have each element as its own disjoint set. Then we are just initializing the rank of those elements. For the find function, which is implemented over here, what we would check is if the element itself is not the representative of that set, then we have to find the parent. If it's the case, then we just return itself. If it's not the representative of that set, then we call a recursive function. So we call its parent. So this function will be executed until the element itself is the parent of itself, and then that parent will be returned. So here the base case, this is the base case, right? Then let's look at the union code implemented over here. So if you want to union two elements, which is x and y, first we need to find the root of those elements, right? So that's where we call the find function, and then we store that in the root of x and as the root of y. Now, if we are doing union by rank, in that case, we want to merge the smaller tree to the bigger tree. So the tree with the smaller rank, we want to merge it with the tree with the higher rank or the height. So if root of x is not equal to root of y, then union by rank to keep the overall height of the tree shallow so that our find operations are optimized. So for that, first we would look if the rank of x is greater than the rank of y. In that case, now we want to merge y to the x tree, right? So then we say that the parent of root y is equal to root x. Else if it's the other way, if the rank of x is smaller than rank of y, then now we want to merge the tree with root as x to the tree with root as y. So then we say that the parent of root x is equal to root y. Else, now if the parent of root y is equal to root x, then in that case, if both of our trees are of exactly the same rank, then in that case, what we would do is we would pick any tree, merge it with the other tree. But now, because both the trees are of same rank, the total, the final resulted tree will be of one rank higher. So if we just quickly look this with an example, let's say if we have one tree with two elements, and if we have other tree with 3, 4, 5, 6. Now, if we are performing the union operation, in this case, the rank of this is 1, rank of this is 2. So we will be merging the smaller tree to this bigger tree. And the final outcome tree would look like 3, 4, 5, 6 with 1 and 2. Now, in this case, the rank of this final tree still remains whatever it is initially, right? 2, because we are merging the smaller tree to the larger tree. So the rank does not increase. So we don't have to do this step for these both conditions. But if both these trees are of same height, for example, if both these trees were, let's say the tree is only till here. Now, in this case, the rank of both these trees is 2, is 1, right? So now in this case, the doesn't matter if we merge the first tree with the second or the second with the first. Let's say we merge second with the first. Then in that case, our final tree would look something like this: 3, 4, and 5. So now the final rank of this tree is 2, right? Not 1, because already the rank of tree by itself was 1 and we added one more tree to that. So that's why this step is only in that last condition. Right, so now let's walk through with the use case of this example. So let's say we give the input command, the disjoint set of 6. This would create us 5 different elements. Let me erase other stuff on the screen. Okay, so now we have 5 different elements after the first command, 3, 4, and 5. We are doing union of 1, 2, which joins this both, union of 2, 3, which joins 3 to the representative of the set, union of 4, 5, which joins this both. Now we are doing print find 3. So that would print the representative of that set, which is 1, right? If we do print find 5, that would print the representative of that set, which is 4. If we walk through the code in this case, union of 1, 2, so the set 1 and 2, the root of 1 is 1 if it's just single element in that. The root is 2 by itself. Now, if both the root is not same, yes, they are not same. In that case, if the rank of x greater than y, which is not true, rank of x smaller than y, which is not true because both the sets just have single element in them. So we will end up into this condition for this first statement. So now in this case, the we would merge the second, which is 2, with 1, right? And then we would make the rank of this tree from 0 to 1. Now we are doing union of 2, 3. So now we have this 1, 2, and 3 is independent element. In that case, now we would end up in which if condition? The first one, right? Because the root of x, which the rank is 1 in this case, and the rank of the second tree is just 0. So that's why inside the first if loop, now we say that the parent of the root y is equal to root x. And hence we find the parent of 2, which is 1, and then we make that as the parent of 3 itself, right? So which is this thing that we did over here. And then we have another union statement, which is union of 4, 5. So we execute that as how we executed union of 1, 2, union of 2 independent disjoint set, each with just one element. And then when we do find of 3, let's look at the find algorithm quickly. So find of 3, what would happen is if the parent of 3 is not equal to 3, yes, it is not, the parent of 3 is not equal to 3. The parent of 3 is different. So that's why we would enter this if loop. Then we would search if the parent, we would search to the parent of 3 and call it recursively until we find the parent of that element is equal to itself. So this recursive loop will execute one time over here until we reach 1. Once we reach 1, then the parent of 1 is equal to 1. So in that case, it will exit this if, and we would just return 1, right? So we would return 1, which is the answer to this first find. In the same way, we would execute the second find of 5, which would return 4. Do you know how to use this joint set? What's the use of the data structure if you don't know how to use it? Or what are the practical applications of it? Right? So let's learn Kruskal's algorithm for minimum spanning tree, which is one of the practical application of disjoint set. So for people who are hearing MST as the new term, and you don't know what it is, let me give you a brief example. So let's say if we have a graph with 4 nodes and we have just random edges connecting them. We have some edge weights to 7, 9, 3, 8. Now, a minimum spanning tree for such a graph would be having all the edges, but we have 3 important conditions. One, there is no cycle in the minimum spanning tree, hence it's a tree, not a graph. Second, all the edges of the minimum spanning tree sum to the minimum number, right? So we want to connect all the vertices with the edges that are of least weight. Third, minimum spanning tree should have all the vertices of the graph. So we have all the vertices. Now, if we have to draw a minimum spanning tree for this example, we would have this edge with weight 2. We would have this edge with weight 3. Now, in order to connect 3, if we connect edge between 1 and 3, it's of weight 7, versus if we connect edge between 3 and 4, it's of weight 9. So 7 is smaller than 9. We would go here. And we will not connect the edge between 2 and 4 because that would make a cycle. And also will not connect an edge between 3 and 4 because that would make a cycle. So this is the minimum spanning tree for a graph like this. Now we could use disjoint set to code something for minimum spanning tree. But before we jump on how to code for that, let's just look or think of some of the practical applicabilities of minimum spanning tree itself. So where you would use a data structure, or where you would use something like this. Let's say, for example, we are working on grocery distribution app, where the goal is to route the vehicle from the grocery store to all the customers in a way that it consumes least possible fuel, or in a way that it's like minimum possible miles, but you want to deliver to all the customers. So in such an application, we might be able to use minimum spanning tree, because there we are forming a graph with the edges that has minimum weights, with weights being the miles or the distance between the grocery store and the customer itself. In the same way, the minimum spanning trees have a lot of applicabilities ranging from network design to transportation to clustering, etc. So now with that in mind, we know that it's something very useful. Let's see how to code for minimum spanning tree and Kruskal's algorithm using disjoint set. Okay, so let's first look at different steps that you see here on the left. So the first step of Kruskal's algorithm is to sort all the edges, where we would just list all the edges or between all the vertices of the graph, and we would sort them from minimum to maximum. Then we would initialize union find. You already learned about union and find operations earlier in this lecture. And finally, we would process the edges, right? So we would process the edges in the way that we construct a minimum spanning tree, and then we would terminate to give the output of the minimum spanning tree. Now, let's do a walkthrough to a specific example so that it's even more clear. So if you want to draw the graph of what the example that you see on the left, that has 4 edges again, that would be edge 0, 1, 2, 3. Edge 0 and 1 is connected with weight 10. Edge 0 and 2 is connected with weight 6. Edge 0 and 3 connected with weight 5. Edge 1 and 3 is connected with weight 15. Edge 2 and 3 is connected with weight 4. So this is our graph. Now, to proceed with Kruskal's algorithm, first step, sorting the edges. So if you want to sort all the edges that we have over here, we would end up with this list, right? Where 2, 3 is the edge with the minimum weight. Then the vertices 0 and 3 are joined with the edge with the weight of 5, 6, 10, and then 15. Then we initialize our union find. So for this, we would need the parent and we need the rank. So we take each of these vertices of the graph as a set by itself, as a disjoint set by itself, with themselves being their own parent. So in that case, the parent would be 0, 1, 2, 3, and the rank, because each of this is a tree with 0 height. So the rank would be 0. Now, then we move to the step of processing edges. So first we process edge 2, 3, because that is the one with the smallest weight, right, over here. So first we process that. So the roots of 2 and 3 both are different. The root of 2 is 2 and the root of 3 is 3. That's why we add that to our minimum spanning tree. Let me draw our minimum spanning tree over here. We add that to our minimum spanning tree. And we do the union of 2 and 3, right? So if I'm just maintaining the union find structure over here, so we do the union of 2 and 3. The edge weight of 2, 3 is 4. So in the minimum spanning tree, this would be 4. Next, how does this change this operation that we did? How does that change our parent and rank matrix? Is now the parent of 3 is 2. Let's say that the 2 is representative of this set. So we change that. Yeah. Okay, got it. Figured it out. Nailed it. So the parent of 3 now becomes 2, and the rank of 2 becomes 1, right? Because now 2 is a disjoint set with rank of 1 or height of 1. Then we keep on adding other edges that we have in our sorted edge list. So then our next edge is 2, 3, as we see over here, 0, 3, as we see over here with the weight of 5. For 0, 3, we would look if 0 and 3 has two different, so now this both is connected, right, in our minimum spanning tree progression, which is this one after the state. And just keep the states. So now if we look at the parent of 0, which is different from the parent of 3, which is 2, parent of 0 is 0. That's why we would go ahead and add that to our minimum spanning tree. So the edge is between 0 and 3 with the weight of 5. And now we will be adding 0 to our union. So we would do union sets 0 and 3, and 0 and 3, it's because the representative of 3 is 2, so we would be joining 0 to 2. This is the union by rank optimization, right? So now the rank of our union find structure over here remains the same. It still remains 1. And the parent the parent array changes as the parent of 0 now becomes 2 rather than itself. So we have that change over here. In the same way, we next add the remaining edges, 0 and 2. So we look at the parent of 0, which is 2, the parent of 2, which is 2. So we skip that. Then the last two edges are edge 0 and 1 and 1 and 3. So we look at the parent of 0, which is 2. We look at the parent of 1, which is 1. Now the parents are different, so we would have to add it. The minimum spanning tree, so we add 1 over here, adding 0 and 1. The 0 and 1 edge weight is 10. And now when we do union of 0 and 1, because the parent of 0 is 2, 1 will be connected to 2. And that changes our parent data structure as the parent of all the element is 2, 0, 1, 3, and 2 itself. And the rank of 2 is 1. Finally, the last edge, which is 0 and 3, the parent of 0 is 2, the parent of 3 is 2, so we will skip that. So we have the result as our minimum spanning tree that you see here on the right. And the total edge weights would be 4 plus 5 plus 10, which is 19 of this minimum spanning tree, which is the output of the code. Okay, so now let's look at the code statements itself in order to ensure that we understand this implementation properly. So we would need, so what the disjoint set initialization, the find, and the union, the code that we looked earlier in this class, we would need that because that's the implementation of the functions union, the functions find, and the function and the class disjoint set. If you do not recall, please rewind it a bit and you would see the explanation of that. Beyond that, now let's see the implementation of Kruskal's algorithm. So first we would define the disjoint set of n. We would define our minimum spanning tree weight as 0. we would define our minimum spanning tree edges as just an empty array or empty list of items. Then our first step is sorting the edges. So we would sort all the edges that we have in the graph, which is given to us. Then we would go into this for loop where for vertices and weights in that sorted edges list, first we would do is find U, which is find the representative or the parent of U, and we would find the parent of V. If they are same, then we just skip. If they are not same, then we do union of U and V. After we do the union of U and V, we append the edges of minimum spanning tree with UV and the weight of that edge, and then we add the minimum spanning tree weight to that. So just as a quick example run through, let's say if we have 4 vertices, this is the example that we walked through. And if we have edges such as these ones over here, then how we would call this function would be that we want to call the Kruskal's algorithm with the vertices 4 and the edges that we just defined here above. And we would print at the end, print the edges in minimum spanning tree and print the weight in the minimum spanning tree. And then we just call the main function. And this concludes our implementation of Kruskal's algorithm. Thank you.